Up to this point, we've talked a lot about various solution properties and particularly units of solution concentration. But now we get to the real meat and potatoes of solution chemistry, and this is in the area of colligative properties. So what exactly are colligative properties? Well, it turns out that the properties of solutions can differ greatly from those of just the pure solvent. So if you take water and you think about its properties in terms of its boiling point or its freezing point or its density or any of those properties of that pure solvent, if you then take the water and dissolve table salt in it, the new solution can have very different properties from the pure water. And many of those properties are referred to as colligative properties. So colligative properties are those properties of solution that depend on the number of solute particles, but is completely independent of the identity. So this is a grouping of properties that has nothing to do with what the solute is, and depends simply on the number of solute particles that are dissolved. And so we'll go through several of these. There's actually four main colligative properties or effects. The first is vapor pressure lowering. We'll go through that in just a moment. The second is boiling point elevation, freezing point depression, and finally osmotic pressure. And we will deal with each of these very specifically. These are very important and have huge and abundant applications in our everyday lives. So let's start with the first one, vapor pressure lowering. What does that mean exactly? Well, the presence of some non-volatile solute. So what I mean is some solute that doesn't just naturally evaporate readily by itself. So generally solids are the most ready example, but sometimes we can have liquids providing that their boiling point is high and they're non-volatile. The presence of non-volatile solute particles lowers the vapor pressure of the liquid. So remember, the liquid has some amount of gas of that liquid. Some molecules have had enough kinetic energy to escape from the surface and then exist as a vapor above the liquid, thus constituting the vapor pressure. If we dissolve some non-volatile solute into that solvent, then the vapor pressure of the solvent decreases. We can illustrate that in this example here. So normally you have a solution, or a solvent, I should say, and there's a normal equilibrium between the gas or the molecules of that solvent that have enough energy to escape into the gas form, and then some of those molecules hit the surface and re-enter, but other ones have enough kinetic energy to escape, and eventually you reach this equilibrium where you have a certain vapor pressure then from the vapor that sits above the solvent. If we take solute, non-volatile solute, and dissolve it into the solvent, now there are intermolecular interactions between the solute particles and the solvent. That then reduces the number of solvent molecules that are able to escape. Now there's a new species that's present that's interacting with the solvent, that's attracting those solvent particles or molecules to itself, and we reduce the rate of vaporization, or the rate at which molecules leave the solution to form the vapor phase. Now, the molecules that are in the vapor phase, they haven't slowed down at all, nothing's changed with them, so they begin to collide back with the surface and they re-enter the solution phase at the normal rate. And what that does in the net then is eventually we establish a new equilibrium where there are fewer solvent molecules that are leaving the solution to form the vapor phase, and that now is in equilibrium with the fewer number that are in the vapor phase that are re-entering. And so the net result is that the vapor pressure decreases simply because there are less molecules in the vapor phase. And we can actually quantify this effect in something known as Rayold's law. Now, Rayold's law is written in this way, where we have the pressure of a solution. So this is the partial pressure above a solution that contains solute and solvent. is equal to the mole fraction of the solvent times the initial, or times the partial pressure of the solvent if there were no solute present. So P solution is the vapor pressure of the solvent over the solution. X is the mole fraction of the solvent, and then the P0 solvent is the vapor pressure of the pure solvent with no solute dissolved in it. Let's do two examples to illustrate this. So calculate the vapor pressure of water over a solution that contains 100.5 grams of lactose. And lactose's molar mass is given to us. And we have 200 grams of water at 25 degrees Celsius, and the vapor pressure of pure water at this temperature is 23.76 torr. What we need to evaluate first is what have we been given and what do we need? Well, we've been given the vapor pressure of pure water at this temperature, so that's P0 solvent. So we have that 23.76 torr. That's P0 solvent. And we're asked for the vapor pressure of water over the solution. So we're asked for P of solution. And then we're not given the mole fraction, but we are given information we could use to calculate the mole fraction. So we're given a mass of the solute and its molar mass, and we're given a mass of water. So if we convert the mass of the solute to moles of solute and the mass of water to moles of water, then we can get the total number of moles, and we can calculate the mole fraction we can calculate the mole fraction of the water. So here, 200 grams of water divided by its molar mass gets me 11.099 moles of water. And lactose, here we take 100 grams of lactose and divide that by the molar mass. Now, lactose is a non-ionic compound, so it doesn't break up into multiple particles when we dissolve it in solution. It simply stays as one molecule of lactose, unlike something like sodium chloride, which would dissociate into two particles. So if we're calculating a number of particles, we can say that for lactose, there's just 1 mole of solute particles for every 1 mole of lactose because it doesn't dissociate. So we come out with 0.2936 moles of solute. And so then the mole fraction is the moles of the solvent over the total moles of particles, not just the total moles of solute and solvent, but if the solute were to break up into multiple particles, we have to factor that in as well. So here it's just the mole fraction of water being 11.099 divided by the sum of the moles, and so we get 0.9742 as the mole fraction for water. Now we can substitute that into the above equation and multiply through and calculate out the partial pressure of water over the solution is now only 23.15 torr. So we've decreased the partial pressure of water from 23.76 in pure water down to only 23.15 torr. Let's do another example, one that may involve multiple solute particles. So if we do almost an identical problem, but in this case, the solute is sodium chloride, and we're given its molar mass. In this case, sodium chloride does dissociate into sodium ions and chloride ions. And so we need to account for the total moles of particles when we're calculating the mole fraction. So the process, we have the same number of moles of water. We take the 50 grams of sodium chloride, divide that to get moles of sodium chloride, but we get 2 particles for every 1 mole of sodium chloride because I get 1 sodium ion and 1 chloride ion. So in total, I have 1.726 or 1.729 moles of particles, of solute particles. And so my mole fraction for water is simply the moles of water divided by the moles of water plus the total moles of solute particles. And that comes out with a mole fraction of only 0.8652 for water. Substitute that in now, and we notice that my partial pressure of water has decreased from 23.76 torr down only to 20.56 torr. So this is how we would use Rayold's law to calculate vapor pressure, or if we were given the vapor pressure of the solution and vapor pressure of the solvent, we could figure out the mole fraction, etc. for these. but this is our first colligative property. It has nothing to do with the identity of the solute beyond just whether it breaks up into 2 ions or 3 ions, or if it doesn't break up into any ions and there's 1 particle per solute molecule. Otherwise, there's no dependence on the identity of the solute particles themselves.